Hello Mathies, Gatos here. In this video, we're going to cover horizontal and vertical reflections. Let's get started. A reflection is a special type of a transformation in which each point in a function is reflected along a line of reflection. After we do the reflection, the image and the original point will be the same distance from that line of reflection. When I reflect things, I change the orientation of the graph. Because I change the orientation, I also change the position, but what does not change is the shape. In this course, we're going to look at three types of reflections. We're going to look at reflections in the line y equal to 0, the x-axis, reflections in the line x equal to 0, the y-axis, and reflections in the line y equal to x, the diagonal identity line. In this video, I will only cover 1 and 2. We'll cover 3 a little bit later. When I talk about transformations, often you'll hear me talk about invariant points. And those are points that stay the same even after a transformation has occurred. So we just did translations. Why didn't we talk about invariant points there? If you look at this graph here, let's just look at some basic points here. Let's say I were to do a translation of maybe up 1 and over 3 units to get this new graph. When you look at this graph here, every single point has changed. That's why we don't talk about invariant points. In fact, translations are the only transformation without invariant points because all the points move. When we're describing transformations, in particular reflections, again, proper terminology, no abbreviations, I want you to describe what the transformation is, i.e. vertical or horizontal reflection, and where it is. It's either in the x-axis or in the y-axis. So describe what it is, where it is, and remember, points are reflected in an axis. Let's talk about vertical reflections first. I'm going to use the parameter a, which is in front of the function. When a is positive, greater than 0, there is no vertical reflection. When a is negative, less than 0, there is a vertical reflection, and that occurs in the x-axis. Since it is vertical, the points line up vertical, a only affects the y-coordinate. X-coordinates stay the same. So let's talk about that. Let's say that we have points above the x-axis. Now, points that are above the x-axis will always have positive y values. So if I reflect that, the point is now going to be below the x-axis and it will have a negative y value. For example, this point 1 and 4, this is 4 units above the x-axis. When I reflect it, it becomes 4 units below the x-axis. So what you can see with the mapping notation here is that my x values stay the same. It is my y values that become opposite. Similarly, if I have points that are below the x-axis, where y is negative, when I reflect it, the point will now be above the x-axis, where y is positive. For example, this point 1 and negative 4 is 4 units below the x-axis, so a vertical reflection will place it 4 units above the x-axis. In terms of the mapping notation here, you can again see that your x values stay the same. It is only your y values that are opposite. So to show that in general for mapping notation, every point xy becomes the point x negative y. So again, x is staying the same, y is becoming opposite. This does not mean that the image always has a negative y value. Negative y shows that it is the opposite. Negative y actually means that y is going to be multiplied by negative 1. That's how we make something opposite. So let's look at an example here of invariant points with vertical reflections. Are there any? Let's check. So let's first of all look at points here that are in some of the quadrants. So for example, here, this point that is 2 below, when I reflect it becomes 2 above. This point here in quadrant 2, it's 3 above, reflected is 3 below, and so on. This is 1 above, becomes 1 below. This is 5 above, becomes 5 below. So it looks like all those points changed. And in fact, vertical reflections do not have invariant points in any of the quadrants. Well, let's look at what happens when it's on one of the axes, X and Y. So for a vertical reflection, for example, this y-intercept, I can see that it starts 2 units above, and when I reflect it, it's now 2 units below. If I look at the x-intercept, it is on the line of reflection. It is 0 units away from the x-axis, so it will stay exactly where it is. So vertical reflections do not have invariant points on the y-axis, but they do have invariant points on the x-axis because that is the line of reflection. So all the x-intercepts are going to equal to invariant points when it comes to vertical reflections. Let's look at an example. Here I have my original function f of x above the x-axis and my transformed function g of x below the x-axis. So the first thing I can see is that these points line up vertically. So above to below, lining up vertically tells me I have a vertical reflection in the x-axis. Since it's in the x-axis, any point on the x-axis, in other words, x-intercepts, will be your invariant points. So in this case, the point 0, 0 would be invariant. Now let's look at this graph here in terms of the mapping notation. So we can see that all the points line up vertically, and I can see that all the x points stay the same. So all of your x values stay the same. All of your y values, however, become the opposite value. And the way that we show opposite is multiplying it by -1. So this point xy in general becomes the point x negative y. In terms of your vertical reflection, that means that A is negative, in this case, -1. So my equation is A times f of x, or -1 times f of x is just negative f of x. So when I have a negative on the outside of a function, that tells me there is a vertical reflection. Let's now do the same thing with horizontal reflections. So horizontal reflections, I'm going to use parameter b. So when b is less than 0, in other words, it's negative, when b is greater than 0, positive, there is no horizontal reflection. But when b is less than 0, negative, there is a horizontal reflection that happens in the y-axis. Because this is horizontal and all the values lie up horizontally, b only affects the x coordinate. Y will stay the same, x is what's changing this time. Let's talk about how that works. So points to the right of the y-axis. So points to the right of the y-axis have positive x values. When I do a horizontal reflection, the point will now be to the left of the y-axis and have a negative x value. For example, here, this point here is to the right. The x value is 1. It's 1 unit to the right. When I reflect it, it becomes 1 unit to the left. So my mapping notation is that x is now the opposite value, y stays the same. Similarly, if I have points that are to the left of the y-axis, those have negative x values. When I horizontally reflect them, instead of being to the left, it will now be to the right of the y-axis, where x is positive. So for example, -1 and 4 is 1 to the left. When I reflect it, it becomes 1 to the right. Again, with my mapping notation, it is only x that changes to become the opposite value. Y stays the same. So in general, when I have a horizontal reflection, all of my points xy are going to become negative xy. Y stays the same, x becomes the opposite. Again, this does not mean that in my image point, all of the x coordinates are negative. That negative x really just means that x is multiplied by -1, and that's how we create something with an opposite value. Let's talk invariant points now. Do horizontal reflections have invariant points? So let's look at these points here. So this point right here is 5 to the left. When I reflect it, it will be 5 to the right. This one is reflected 2 to the right. This one here is 3 to the right. Reflected becomes 3 to the left. This point here, 4 to the right, reflected horizontally, is 4 to the left. So it looks like when I have points that are in quadrant, horizontal reflections will not have any invariant points in any of the quadrants. Let's look if that's the same for the intercepts. So looking at the x and the y-intercept, reflecting horizontally. This x-intercept is 4 to the left. When I reflect it, it becomes 4 to the right. So that does not stay the same, it changes. This y-intercept is 0 units from the y-axis. It's on the y-axis, so it will stay the same. In terms of horizontal reflections, they do not have invariant points on the x-axis, but they do have invariant points on the y-axis. Why? Because that is the line of reflection. So when it comes to horizontal reflections, y-intercepts will always equal to invariant points. Okay, let's look at an example here. So I have my original function f of x, my image g of x. I can see that this time the points line up horizontally. Since they line up horizontally and are the same distance from the y-axis, I know that I have a horizontal reflection, that's what it is, and where it is in the y-axis. Since the reflection is in the y-axis, invariant points will be any points on the y-axis, or in this case, y-intercepts. So the y-intercept of 0 and 9 would be an invariant point. Let's look at the mapping notation. So lining all our points up, these are the key points that I reflected. I can look at my mapping notation from original to image. In this here, I can see negative 3, 0 became 3, 0. I can see my y values all stayed the same. So y values are staying the same. And if I look here, it's the x values that are opposite. So in terms of my mapping notation, I want to show that x is opposite, negative x, and y stays the same. So because this is a horizontal reflection, it is b that is less than 0. We'll call it negative 1. And in terms of my equation, I have f of negative 1 times x, which is just simply g of x is negative x. So when the negative is on the inside, that is a horizontal reflection. So let's put this together and do a question where we're graphing, doing two different types of reflections. The first one here, look at the negative, it's on the outside. I want to graph, given the function of f of x, negative f of x. So since the negative is on the outside, that tells me I have a vertical reflection in the x-axis. So that means any point that is below the x-axis is reflected to be above the x-axis. Any point that is above the x-axis is reflected to be below. Now, because we're reflecting in the x-axis, anything on the x-axis is invariant. It does not change. So I just have to connect my dots, and that is the graph of negative f of x. Similarly here, I'm going to take that same graph of f of x, and I'm going to graph y equals f of negative x. So this time, the negative is on the inside. With the negative on the inside, that is a horizontal reflection in the y-axis. So let's look compared to the y-axis. Any points that are to the left of the y-axis are reflected to be to the right. Any points to the right of the y-axis are reflected to be to the left. In terms of my intercepts, my x-intercepts change, but because this is a horizontal reflection, anything on the line of reflection, the y-intercept stays the same. Then I just connect my dots, and there is my equation, y equals to f of negative x. So that is a horizontal and a vertical reflection. I just want to end with one last example involving equations. So this time I'm given the equation, f of x is negative x cubed plus 2x squared plus 7. I want to reflect it in both the x and the y-axis. So a vertical and a horizontal reflection. So that means that x is the opposite value and y is also the opposite value. So first of all, let's do that in terms of f of x. That just means in general for any function. So we'll start with y equals to f of x. We're going to replace our x with negative x and our y with negative y. So I end up with negative y equals f of negative x. Now I don't want a negative y equals equation. I want a y equals equation. So I'm going to divide both sides of the equation by negative 1. So on this side here, I have negative y divided by negative 1, which is just positive y. On this side here, there's really an imaginary 1 in front of there. We don't normally write it, but it helps us see that 1 divided by negative 1 is negative f of negative x. So negative 1 times f of negative x is just simply negative f of negative x. So the negative on the outside shows it's vertical, the negative on the inside shows it's horizontal. That's in terms of f of x. Let's look at how we do it in terms of x, which is specific to one function, namely this cubic function. So I'm going to start with my original equation. And similarly, I'm going to replace my y with negative y and my x with negative x. I have to use brackets when I make that substitution. So over here, I still just have negative y. Negative x cubed is negative x cubed, and negative x squared is just positive x squared. So here, I'm going to multiply these two negatives together. Negative 1 times negative 1 is positive 1. And then 2 times x squared, 2x squared. Again, I don't want a negative y equals equation. I want a y equals equation. So I'm going to divide every term by negative 1. So negative y divided by negative 1 is y. And then I just do x cubed divided by negative 1, 2x squared divided by negative 1, and 7 divided by negative 1 to get my final equation, negative x cubed minus 2x squared minus 7. And that shows the reflection in x and y axis in terms of x. So to prepare for this lesson, I really had to do some reflecting. Namely, I was reflecting on math numbers such as pi. And isn't that interesting that if you take pi and you do a horizontal reflection, you still get pi? Does that mean pi is invariant? I'll let you be the judge. So I hope this video helped. If it did, please give it a thumbs up and hit subscribe so I can help more mathies just like you. Thanks for watching, and I'll see you for the next one.